Today we're going to look at derivatives as functions. So we're going to estimate some derivatives from graphs, and we're also going to define what makes something differentiable or not from its graph. So first we want to do this example, and we're going to sketch a graph of a function g for which g of 0 is equal to 0, g prime of 0 is equal to 3, g prime of 1 is equal to 0, and g prime of 2 is equal to 1. So the first part here, when we're looking at this particular problem, g of 0 is equal to 0 is giving me a coordinate point on this graph. The other pieces within this, the other pieces are giving me slopes. So if you notice, only one of these is actually a point on my graph. The rest of it is saying, how does the graph behave? What is the steepness of the graph? I'm going to start with my g of 0 is equal to 0. Okay, and then I have g prime of 0 is equal to 3. That means the rate of change, or the derivative, at 0 is 3. So it should be fairly steep. So we want fairly steep. Okay, and notice I'm just sketching this. Then I want g prime of 1 to be 0. That means it's going to be horizontal here. And then g of 2 is going to be at 1. So this is going to flatten out here. Some point it's going to have to turn and be back to a steepness of 1. Now you might have a sketch that just had it this was one option, okay? You might also have one that had similar flattened and then didn't have that dip. It's another option. We don't have enough information to tell if it did that yet. A way that a problem would have more information would be if it gave you what g prime at 1.5 was, things like that. Use the given graph to estimate the value of each derivative of the slope of the graph, and then sketch the derivatives graph. So f prime of negative 2. At negative 2, use the graph to estimate the value of each derivative, the slope of the curve. Then sketch the graph of f prime. So we want to find f prime of negative 2, f prime of negative 1, f prime of 0, f prime of 1, and f prime of positive 2. So we'll start at negative 2. And I kind of sketch a tangent line. That to me looks like it has a slope of negative 2. Then at negative 1, I do a little sketch about estimating that tangent line, and that looks like about negative 1 for our derivative. At 0, we have a horizontal tangent, so we'll have equals 0. And then positive 1. And positive 2. So the second part of this says actually sketch the derivative. So the derivative is going to look like this. It's going to go through 0, 1, 2, negative 1, negative 2. Just like that. Okay. Next one. We have f of negative 2, f of negative 1, f prime of negative 2. So f prime of negative 2, that's fairly flat line, so I'm going to estimate that as negative 1/4. And f prime of negative 1, say about negative 1. F prime of 0 does not exist. And you can see because I have a vertical asymptote on this rational graph. So if the function doesn't exist, how could its derivative exist? F prime of 1 is negative 1 again. And f prime of 2 is about negative 1/4. So then when I sketch these, it'll be negative 1, negative 1/4, negative -1. Actually, I should have changed colors. The actual derivative. So this one's getting steeper, headed down that way. This one's going down that way. Okay. Alright. Next one. F prime of -3. That is down here. Yeah. Horizontal tangent, 0. F prime of -1. Right around there. We'll say like 2. It looks a little steeper. F prime of 0. This is a tricky one because on this, it's this way. So from the left, it's approaching infinity, and from the right, it's approaching infinity. So this does not exist. F prime of 1. Let's see. And f prime of 3 is equal to 0. Okay. There are 4 ways, and you can see in the last 2, we had 2 different situations where it doesn't exist. One because the function was not defined, and one because those 2 sides were both approaching infinity. So there's actually 4 in total. The first one's called a cusp, and that's actually what we just looked at. And here's another example of a cusp. And you can see that you have this steepness, and you're approaching infinity on both sides, but you kind of come to a single point rather than a vertical asymptote kind of situation. Okay? And you can see that, like, on this side, the slope is negative, and on this side, the slope is positive. Corner, this happens to be a 90-degree corner, and this one, the left-hand slope is going to be +1. Here, the right-hand slope is equal to -1. And so, as I'm approaching from the 2 different sides, we're not matching with those. Those are called a corner. So both corner and cusp, the left hand and the right hand are not matching up, but on a cusp, it's approaching this infinity vertical tangent situation. Then discontinuity. We had a discontinuity in the earlier slides about what would happen with a vertical tangent. Here we have a jump discontinuity, and that still is not differentiable at that value. And then last but not least is something with a vertical tangent. So this one, even though it's still defined there and you're still approaching, you have this smoothness that it's not a drastic change between things. We still have a vertical tangent line right here, and so it's not differentiable at 0. This is cube root of x, in case you were wondering. And that concludes this lesson.